So the last piece of the puzzle from this example is the test driver implementation, which of course is the LockManagerTest, as well as the code that we'll look at in a second that does the lock API and the server bean that we looked at. That's pretty straightforward. So you can get all this code here in my GitHub repository at this link. So we're now back in IntelliJ again, looking at the LockManagerTests portion of the program. And let's just take a quick look. Here's the lock API. I just went through that in some detail, so I won't really spend much time on it, but this is just the code that's used to create an asynchronous endpoint for clients declaratively. So that's really nice. We have our client beans class that has the factor method that makes the lock API using the mechanisms that are built with the web client and the HTTP interface stuff, which is this HTTP service proxy factory. And now let's go ahead and take a look at the tests themselves. So the test is a Spring Boot test, no surprise there. It's going to be launching the LockManager application microservice automatically using the port that's defined. We auto-wire in the lock API using the bean to manufacture that. And then we've got a couple of fields here. We have one that keeps track of how many permits we want to acquire when we're acquiring multiple permits. We keep track of the number of locks we want to have our distributed semaphore create and manage. We keep track of the number of clients. This is all really the same as the previous example we looked at for Spring Web MVC. But now let's take a look at the test code. So this is the piece of code that runs automatically. It's a JUnit test that will test single acquire and release calls. And you can see how we use the Fluent programming style for reactive programming to do this. So the first thing we do is we say, lock API, I want you to go out and create me a distributed semaphore with max locks items. So it'll go, and that'll make the remote procedure call, remote method invocation call over to the microservice. And that gives us back, as you can see, a mono to Boolean. So when that call is done, the mono will emit Boolean, either true or false. And we just note whether it is true or false, whether it changed anything. The first time through, it'll change stuff because it's making it anew. Then we go ahead and we make a flux, and we run the flux from 0 to max counts -1 iterations. And each time through, we're going to call acquire and release single locks using flat map. And we're going to collect the results into a list of void. And, collect it into a list of void. And this thing will return a mono to a list of void. And then we block until all this asynchronous processing is done. Each of these calls here, as we'll see when we look at this, runs in its own thread of control on the client side. And I probably should use virtual threads over here too. If I was really clever, I would set this up to use virtual threads, which I think I can do. So let's go take a look at acquire and release single locks. This once again shows how to use the Fluent programming style. So we come in here and we call the acquire method on the lock API. And you can see that returns a mono to a lock. So that will go ahead and make the call, get back a mono to a lock. Now, in this particular case, what we say is, whenever that completes, whenever we've actually got a lock, go ahead and print out what the lock was. And then what we're going to do is we're going to use flat map to release the lock asynchronously. So this call gets called back when we get ourselves a lock. When we're done printing out the log message, flat map gets called. It takes the lock, which is now a list, because that's what we got back from acquire. I'm sorry, we got back one. We got one lock back. We release that one lock. That returns a mono to a Boolean. If that succeeds, we print the lock that was released. If something were to go wrong, if an exception was to occur, we would go ahead and print the exception message. And then what we do is we use the .then suppressing operator to tell the caller we're done. So it knows that it can wrap up if we're the last one that's running. And of course, there's 4 of these things running in parallel. And these calls are all taking place in different threads. You'll see that when we run the program in a second. So let's go take a look at test multiple acquire and release. And you can see it has a very similar structure. We create the lock asynchronously, get back a mono to a Boolean. When that completes, the mono emits the Boolean. We log what happened. If this is the second call, this will probably indicate that the value had not changed because we have the same count for max locks. We then go ahead and have this little sort of a for loop-like thing going on where we call acquire and release multiple locks and collect the results into a list of void and then block waiting till all those calls are done. And if we come down here and take a look at acquire and release multiple locks, it looks pretty much like acquire and release locks, the only difference being that we acquire multiple permits. And then we go ahead and we get multiple permits, we collect the locks into a mono to a list. So we call acquire, that gives back a flux of locks. We get a mono to a list of locks by using collect list. Then we use flat map to go ahead and release all those locks, and same basic structure for handling success or failure. So you can see this is all fully reactive on the client side. So let's go ahead and run this thing. And as usual, it spits out a whole bunch of messages, so I won't walk through them in gory detail, but I just want to give you the highlights of all this stuff. Let's see, it's probably in the midst of building right now. There you go. You can watch it build if you want to see it build. We don't really care if it builds. We just care that it builds. And there we go. Now the tests are running. You can see that the test multiple acquire and release actually happened to run first. And you can see on the server side, all the server requests are handled in virtual threads. If you see a thread that's not a virtual thread, it's a client printout, although I think I can change that to make it be cleverly virtual threads on the client side too. And you can see on the client side that we're running these things, all these calls are coming out of the same thread initially, but then as we're going down through here, you can see that the server side is running the threads in a different way. And the client, you can also see that the client doesn't actually have multiple threads going on because it doesn't need them. Since it's reactive, it can just use one thread. It can just use a single thread. A couple other things to note here. Here the request is coming into the controller to acquire 2 semaphores. That forwards to the service. And you can see these are now running on different virtual threads. And you'll also notice that we're going to go ahead and, let's see, this comes back to the client side and indicates that we in fact did get 2 locks. Also interesting to notice how the locks were acquired. So you can see that what happened here was that we got lock number 1 and number 2 in this semaphore, and this one got lock 0 and lock 3. So chances are there had to be some, a little bit of releasing going on in the background in order to get those locks done properly. I don't have printouts for that, but it would be fun to see what it's doing if you want to see the details of how it actually works in a non-blocking way. And then when we're done, we give back the locks, and they're released back into the distributed semaphore count. So again, just looking through this stuff, you can see we acquire multiple locks. The only difference with the single version is it just acquires 1 lock at a time and releases 1 lock at a time, but the same basic flow. So anyway, that's the end of this example. Hope you can now get a better sense of what is required to make your blocking synchronous code that used conventional Java types like lists and Booleans become more fully reactive using monos and fluxes so that we can have a system that is asynchronous from stem to stern, top to bottom, as it were.